Hello everyone, welcome to my YouTube channel. This is Enoch's Tutorials. Don't forget to like this video and subscribe after watching so you can receive every bit of update from this channel. In today's video, we are going to look at what is meant by acid-base titration. That is an important concept in chemistry. So basically, if you want to find the concentration of an unknown solution, you can do so by comparing it with a known solution. So in the lab, we have what we call a standard solution, and a standard solution is that which is having a known concentration. Some cases, if you have a solution of unknown concentration, you can go for it to compare the concentration of the unknown solution to that of the known. And one important concept that allows us to do this principle is what is meant by titration. So we are going to look at the principle behind titration and the basic experimentation, or let's say the setup for titration. So then what is titration as a term? What is meant by titration? When you say titration, what does it mean? So this is a picture of titration setup in the laboratory that shows the various apparatus. Important apparatus include the retort stand. We can have the various flask. Here we have two reagents, one is known and one is unknown. So we are having the sodium hydroxide, which is assumed to be the known concentration or the solution of a known concentration, and the HCl, which is the unknown. So this is just a brief experimentation setup of titration in the laboratory. So let's continue. What is then meant by titration? So basically, when you say titration, it is a chemical analytical process. So the important term is a chemical analysis. That is, it is used what? For chemical analysis. So in which the quantity of some constituent of a sample is determined by adding it to a measured sample of an exactly known quantity of another substance. So what does this all mean? So here what it means is that it is a chemical analytical process in which the concentration of a known solution can be used to find the concentration of an unknown. So we can add the concentration, or we can add the solution of an unknown concentration to that of a known concentration to find its concentration. So if you have two solutions, one having a known concentration and one having an unknown solution, we can mix them together, and through the process it can help us to find the concentration of the unknown, and that is what titration helps us to determine. So the process is gradually, or is carried out gradually, by adding a standard solution. When we say a standard solution, so a standard solution basically is a solution that is having a known concentration. So basically stock solutions in the laboratory are known as standard concentrations, because standard solutions, because they are having known concentration. So the standard solutions are what we call a titrating agent. So they are the ones that are used to titrate. So we assume they are the ones that have a known concentration, and we use them to find the concentration of the unknown solution. So we call the standard solutions or the stock solutions a titrating agent or reagent, or we can also call them what? Titrant. These ones normally run from a burette. So this one normally run from a burette, as we showed in the previous slide. That is just a long and a graduated cylinder with stop clock at the tip that delivers the sample to a receiving flask. That is very simple. So the addition is stopped when the equivalent point is reached. So we're going to look at the meaning of all these terms so we can understand better the principle behind titration. Now, because this principle uses volumes of two solutions, we can also call it a volumetric titration. Volumetric titration. So let's look at some few experimentation, or let's say diagram of how titration is carried out. So basically, if you want to carry out titration, that is to find the solution of the concentration of an unknown solution using that of a known solution, this is how basically we mount the setup. So we have this long stand here, we call the retort stand. Then we have this one we call the clamp. Then the clamp holds in position what you call the burette. So the burette is just a graduated flask as shown here. So the burette is what we put in the stock solution, or what we put in the solution of the known concentration. Then the tip here is the tap. that opens and closes to allow the titrant to flow in down to the receiving flask. So we put in this flask, like this flat bottom flask, or let's say this volumetric flask rather, the analyte. So the analyte is put in a flask like this. So the analyte is the solution whose concentration is unknown and you want to determine through titration. So that's how basically titration is experimental or set up in the laboratory. It's very simple. We are going to look at how it is being mounted well in the next slides. So let's look at some few basic terms in titration. So these are the common terms used in titration that if you don't understand, you may get confused in the process. So when we say an acid, so I think we know. So an acid is just any solution, or let's say any compound that tends to give out a proton in a solution or in water. When we say a solution is acidic, so this is just an adjective form of the acid. It means it can donate a proton to a solution, or it has a pH of less than 7. So a base, just as a term, is any compound or let's say any substance that can accept a proton, and the basic solution is that which can accept a proton, or that which has a pH of greater than 7. And when we say a buffer, so a buffer is just a solution that can resist a change in pH. Basically, it's composed of an acid and its conjugate base. So when we say a conjugate base, whenever an acid loses a proton to an environment, the resulting ionic acid is called a conjugate base. So that conjugate base creates a moderate pH that resists change in pH of the solution. So if a solution can resist a small change in pH, that solution is what we call a buffer. Let's look at the conjugate acid. So a conjugate acid is when a base accepts a proton. The resulting ionic compound from a base accepting a proton is described as a conjugate acid, and its opposite is called a conjugate base. So the conjugate base therefore becomes a compound formed whenever an acid donates a proton. So if I have, let's say, an acid like, let's say, H2SO4, like sulfuric acid, if this compound donates a proton, which is a hydrogen plus, the resulting compound is an ionic form. The ionic form of this, when it gives out a proton, is what we call a conjugate base. Conjugate base. Now, in titration, two important terms normally used that if you don't take it, you can get confused. At this point, we have what we call an endpoint and an equivalent point. So basically, as shown in the previous slides, what happens is if you want to carry out a titration, you have to be able to know a point in time where your analyte has been consumed. So you are going to use a particular volume of your analyte. So if you keep adding the titrant, it will get to a point where the analyte is going to be consumed. Now, that consumption point is normally determined by what we call an indicator. So we add an indicator to every titration reagent to what determine the completion of the titration process. So the point where the indicator changes color, which you are going to see also in the experimentation, the point where the indicator tends to change the color is called an endpoint. An endpoint. Now, because the titrant is added in drops, it will keep changing the color, keep changing till all the volumes or the amount of the analyte in the flask is consumed. So when the amount of the analyte in the flask is consumed, now we say the reaction has gone into completion, and that point is what we call an equivalent point. So the equivalent point is the point where the reaction has gone into completion, or inversely you can say it is the point where the amount of the analyte has been consumed by the added amount of the titrant. But the end point is the point where there is an observed color change. So this means that during the process of titration, the end point is normally observed before the equivalent point, because normally the indicator tends to start changing color before the reaction gets into completion. Now, so these are some basic terms in acids. You have a pH. The pH, which is the power of hydrogen, is just a measure of hydrogen concentrations, hydrogen ion concentrations in the solution. We have pKa, which is an acid dissociation constant, which measures the strength of an acid. We have the pKb, which is what the base dissociation constant, which measures the strength of a base. We can have a strong acid. A strong acid is that which has a pKa of less than 0. Then a strong base is that which has a pKb of less than 0. So strong acids basically totally dissociate in water. That is, they give out all the hydrogen ions they have. And strong bases also dissociate in water. That is, they accept or they give out hydroxide ions completely in water. Let's look at these terms too. We have what we call the titrants. So in the experimentation, the solution of the known concentration that is used to quantify the unknown is called a titrant, or the titrant, or it can also be called a titrating reagent. So let's say if you have a stock solution of sodium hydroxide to determine the unknown concentration of HCl. Now the stock solution is called a titrant or titrating reagent or titrant. Then you have a titration, as we defined earlier. We have required titration curve, which is just a plot of solution's pH versus the volume during what titration. We have weak acid, we have weak bases, which are all well defined here. Another important term which wasn't defined here is what we mean by the titer value. The titer value, an important point. So basically what happens is if you keep titrating, or let's say adding volumes of the known concentration, known solution to that of the unknown, the volume of the known concentration or the known solution that can completely neutralize the unknown is what I mean by the titer value. So we are going to look at it. Let's see if I can get something like this in the video. So we are going to now look at an acid-base titration in detail. So this is just an experimentation which involves 3 steps of a simple acid-base titration. So we have here 550 ml burette which contains an aqueous sodium hydroxide of accurately known concentration. So if the sodium hydroxide is that which is having the known concentration, then the sodium hydroxide is the one called the titrant or the titrating agent. So we assume the NaOH, which is sodium hydroxide, is what? The stock solution, or the one that we assume we know its concentration. Now what happens is, if you want to use this sodium hydroxide to find the concentration of an unknown solution, like let's say an acid like HCl, you are going to fill the burette here with what? A known volume, or let's just fill here with a volume of the sodium hydroxide and put in this flask, being it any flask like round bottom flask, flat bottom flask, or if volumetric flask here, also known volume of what you analyze. So let's say you want to use sodium hydroxide against HCl. What happens is you are going to fill this flask with HCl, then fill the burette here with the sodium hydroxide. Then you are going to add what you call an indicator, which is normally in acid-base titration we use phenolphthalein. We are going to look at this structure in the next slides. Phenolphthalein together with what? The analyte. The analyte is what you put in the flask. You add the analyte together with what? The HCl, which is what? The analyte together with the indicator, so that it can determine the end point as well as the equivalent point of the reaction. Now what happens is if you have a solution of sodium hydroxide, you add it slowly to the sample that is being analyzed. So here the sample, we assume the sample is what? HCl. The HCl is put in this flask. So you add the sodium hydroxide slowly in the flask here. So as you keep adding, you see that the color of the phenolphthalein, which is initially colorless, will now start what? Changing. Or let's say any indicator will start changing from here to here. Now when the amount of the sodium hydroxide added from the burette equals the amount of the hydrogen ions supplied by the acid which is being analyzed, which is in this case HCl, the indicator will change the color. So here we can see that the indicator has a neutral color, but as you keep adding the sodium hydroxide to the analytes in the flask, the color will keep changing from the neutral color to what? Seen here. Let's look at something. So this is just a simple chemistry behind titration. So we want to look at what happens and the color changes. So what happens is that if you add the sodium hydroxide to the flask containing your acid which is to be analyzed, this sodium hydroxide will keep neutralizing all the acids here. So it will keep neutralizing the hydrogen ions in the flask till it gets to a point which is towards what? The alkaline pH. Now at that pH, that is where we assume when all the sodium hydroxide, or let's say when all the HCl in this flask is consumed, we assume that the moles of the sodium hydroxide that has consumed the HCl here are the same. So at this point of equivalent point, at this equivalence point, we say the moles of the sodium hydroxide is equal to the moles of what? The HCl. So at the equivalent point in a neutralization reaction, the moles of the acid, which is the one to be analyzed, is equal to the moles of the base. So let's look at some calculations here. So at the equivalent point, the moles of the acid equals the moles of the base. So let's have this simple equation. So the moles of the acid, which we assume it is Na, is going to equal to the moles of what? The base. That is what happens at the equivalent point. Now the volume of the base that was able to neutralize the acid to the equivalent point is what we mean by the titer value. So in simple calculation, what happens is if you fill this burette with, let's say, 500 ml, 50 ml of sodium hydroxide, then you keep titrating, then let's say at a point of 30 ml, you realize that the color has changed. It means the difference between 30 and 50 is what? 20. So that the volume which was able to reach the equivalence point is what? 20. So that 20 is what we mean by the titer value. The difference between the initial volume and the final volume is what? 20. And now that 20 becomes the titer value. That is the volume of the titrants that is needed to neutralize a known volume of what? The analyte in the flask. So what we want to look at is the solution, the concentration. So at the end of the day, we can determine the titer value, which is the volume of the analyte or the volume of the titrant that is needed to neutralize all the ions or the hydrogen ions in the flask. Then we also know the concentration of the titrant. We also know the volume of the analyte. So what we are left to find is what? The concentration of the analyte. That is why you can use this expression here. Now in mole concept, we know that the moles of a solution, moles, is given by the molarity times what? Volume here. So it means that this concept of the acid is equal to the same concept, which is concept of the base. So when I say the moles of the acid equals the moles of the base, the moles of the acid can be determined by what? The molarity of the acid times the volume of the acid equal to the moles of the base, which is the molarity of the base times the volume of the base. Normally you say the molarity, which is molar concentration, is given by what? The number of moles over what? Volume. So from this expression, that's where we can get the number of moles to be equal to what? The molarity times what? The volume. So with this number of moles of the acid and the same number of moles of the base, these two becomes the same at the equivalent point. So if you use this expression, and you want to find the volume or the concentration, which is the molarity of the acid, we can find this one using this expression because we can know the volume of the acid, which is the volume that you put in the flask. We know the molarity of the base, which is the concentration of the base we used, and the volume of the base to which is the titer value of titration. So the Ma is the molarity of the acid, and the MB is the molarity of the base. Now the VA and the VB are the volumes of the acid and the bases respectively. For us, the acid of the base, which is the VB, is what we mean by the titer value. So that's how basically we summarize titration. It's very simple if you understand the concept. So let's look at a simple calculation here and see how best we can apply the knowledge in titration to calculate the volumes or the concentration of an acid. So let's suppose that titration is performed and 20.7 ml of the 0.5 molar sodium hydroxide is required to react the endpoint when titrated against 15 ml of HCl. So here, this 20.7 ml is the titer value or the volume of the known, the volume of the stock or the volume of the standard solution. And what is here? So this one is the V, which is the volume of the base. Then 0.5 is the MB, which is the molarity of the base. Now this 15 is the VE, which is the volume of the acid. But the MA, which is the molarity of the acid, is what we are looking for, and that one is unknown. So we are going to just have this expression. If you have MA times VA equals MB times VB, if you make MA the subject from that expression, from the one we saw earlier here, if you make MA the subject, you have to divide it here by the VA. So that's how come we have the VA here. So since we have these values, we can just put the values in here. So the MA is what we are looking for. So the MB is the molarity of the base, which is what, 0.5. VB is the volume of the base, which is for the titer value, which is 20.7. Then the VA is the volume of the acid, which is what, 15.0. So when you do this calculation, you're going to get 0.690, which just means that when you titrate 20 ml of 0.5 molar sodium hydroxide against what, 15 ml HCl, the resulting or the volume or the concentration of the HCl is going to be 0.69 molar. So that's how we do a simple titration calculation. Now bear in mind, the above equation works only for neutralization reactions in which there is what, 1:1 stoichiometric equation between, or the stoichiometric coefficient ratio between the acid and the base. So if when you put the equations together like sodium hydroxide plus HCl, this neutralization reaction, you are going to get what, sodium chloride plus what, water. So this is a typical neutralization reaction. The stoichiometric coefficient here is 1 and that here is what, 1. So here the mole of the acid, you can just use this expression straightforward when the stoichiometric coefficient are 1 1. But if it is 1 2, let's say when you write the balanced chemical equation, realize it is 1:2, then if this one represents that of the acid and this one represents the base, then you are going to just put 2 here in front of this. Then we do everything here. It means if you have 2 of this, it means that the number of moles of the base needed to neutralize the acid is twice. So we need 2 times the number of moles of the base neutralize what? Just 1 mole of what? The acid. Take note. So the one that we use straightforward like this one, this expression only works when the stoichiometric coefficient is 1:1. Let's have this part, which is just titration of sulfuric acid with sodium hydroxide solution. So the apparatus which you need for every titration experiment is this, very simple. You are going to need a pipette to pick known volumes of the stock. You are going to need, let's say, sodium hydroxide solution in the case of what? Sodium hydroxide and sulfuric acid. So here, if you have this one, you're going to have this one as the stock or the standard solution. Then this one is the unknown. We are going to need what? A retort stand and a clamp. We are going to need a measuring cylinder for conveying known volumes of what? Of any of the samples. Then we are going to need a phenolphthalein, which is what the indicator that changes color when the reaction reaches what? Endpoint. Then we can have just, let's say, a white paper down there where you can place on top the flask. Now let's look at some observations or the chemistry behind the phenolphthalein principle. Normally the indicator which is used is what? Phenolphthalein. And at the end point, before it gets to the end point, it is colorless, but the color will change from what? Colorless to pink. This one is when you add a base to what? An acid. That is to say, if phenolphthalein reaches a basic medium or an alkaline medium, the color changes to pink. But phenolphthalein in an acidic medium is always colorless. Now this means that it is colorless in acids, but it turns what? Pink when it's base. That's why if you have a flask and you add the phenolphthalein to it, it is colorless. But if as you keep adding the base or titrate with the sodium hydroxide, the pH of this solution will keep increasing, and the point where it try getting to the alkaline medium or the alkaline pH, that is where the color changes to what? Pink. So phenolphthalein is normally what? Colorless in acidic medium, but is pink in basic medium. Now when a specific volume of the sodium hydroxide reacts with the acid, the color is what? Now observed. It is very crucial to stop the addition of the titrant. So as you keep adding the sodium hydroxide, the color changes, and that is what you observed. So when you observe the color, it means that the solution, or the resulting solution down there, is reaching over an alkaline medium. So then you have to stop it. You don't have to keep adding. If you keep adding, the color of the pink will become what? Very deep, and that will not give you the exact amount of what the sodium hydroxide needed. So that can lead to wrong calculations. So as the color keeps changing, just a faint color, you can just stop the reaction and you believe that is the end point or the equivalent point of the reaction. Now the indicator detects the presence of the adequate amount of the base. So as the color changes, the indicator is what tells you that you have enough amount of the base in the solution. So you must pause the titration when it turns what? Pink. If you keep adding it, turns deep pink, that is going to what? Get wrong calculation. Now this is how the structure of phenolphthalein look like. Now this is a phenolphthalein structure. It has an ester link here. So this is a structure in acidic medium. Now this structure in acidic medium is colorless. Now if you add the base, this base is going to cause ester hydrolysis. So this ester bond is going to be hydrolyzed to form a free carboxylate ion. And this carboxylate ion is what results in what? A pink color. So if you keep adding a base to a colorless phenolphthalein, it will tend to what? Pink. And that pink is just the hydrolysis of the ester bond in the phenolphthalein by the base. Additionally, if you have this solution which is pink, phenolphthalein pink, then you keep adding what? Acid, it means you're going to have this what? A colorless compound. So the reverse can be used in case where you have an acid of known concentration and a base of unknown, which is normally not advised. So the reverse can be used if you have an acid of known concentration and a base of unknown. In that case, when you add the pink phenolphthalein to the base in the flask, the color of the resulting solution becomes pink. But if you keep adding the acid, the color becomes what? Colorless. That will indicate the endpoint. But normally it's not advisable for you to add acid to solutions. You have to add other solutions to acids. That's why you normally titrate or use bases. You titrate bases against what? Acids during neutralization reaction. So that's the basic principle of titration. Thanks for watching. Thanks for watching very much. I appreciate the channel. Don't forget to like, subscribe, and also share to whom it may concern so you can receive every bit of update from this channel. Thank you.